Hello everyone. Welcome to another episode of Material Matrix. Welcome. Today we're diving into mechanically. We'll explore just how scattering data combined with GPR and simulations reveals critical parameters like bending and shear forces. This enhances material design, driving innovations across industries from like aerospace to healthcare. Could you explain how mechanically driven polymers behave under external forces and why it is so important to study their scattering functions in the context of extracting physical parameters?
Mechanically driven, polymers are like flexible chains that can stretch and bend when you pull or push them. Like when external forces such as stretching or shear are applied to these polymers, they change shape and size, just like how a rubber band stretches when you pull on it. So understanding how these polymers behave under such forces is crucial because it helps us learn about their physical properties. That's like how strong or flexible they are. Now, when we really want to study these polymers at a very tiny level, we can use special experiments that send beams like X-rays or neutrons to bounce off the polymers. This bouncing creates a pattern called a scattering function, which gives us clues about the polymer structure and how it reacts to the forces. However, the problem is that these experiments alone can't directly tell us the specific details we want to know, like the energy and shape details of the polymers. That's where our machine learning method comes in, We use it to analyze the scattering data and extract important features, just like how much the polymer can stretch or bend by mapping the scattering function to these physical parameters. This process is like solving a puzzle where the scattering data is like the picture on the box, and our job is to find the right pieces that fit together to reveal the hidden details of the polymer's behavior. So under stress. By doing this, we can better understand and predict how these materials will perform in real-life applications.
Can you elaborate on the specific modeling approach used for the polymers, particularly how the fixed-length bonds and bending energy constraints are integrated into the analysis of their scattering functions?
The sort of modeling approach for the polymers is like building a chain made up of sticks that can only connect at certain lengths and can bend at the joints. Each of these sticks represents a fixed length bond in the polymer chain. So when we say there are constraints due to bending energy, it's like saying that the joints can only bend so much before they become too stiff or break. In our analysis, we consider how these fixed length bonds and bending constraints interact when external forces like stretching or shear are really applied. Imagine pulling on a chain of study clips. So if you pull too hard or bend it too much, it will change shape in really specific ways. We use this idea to understand how the polymers actually deform under different forces to study this behavior. So we create a data set using a method called Monte Carlo simulation. This method allows us to explore so many different combinations of energy parameters, such as how much the polymer can bend or stretch. So by simulating these scenarios, we can calculate how the scattering function changes when the polymer responds to the applied force. The scattering function acts like a mirror, reflecting the changes in the polymer's shape and energy when it is really stressed. So we then apply a technique called Gaussian Process Regression to map this scattering function to specific features. So like the bending strength or the distance between the ends of the polymer chain. So this helps us understand the relationship between the polymer's physical properties and how it behaves under a mechanical force. In summary, this modeling approach allows us to capture the essential characteristics of the polymers and analyze their scattering function so effectively.
What role does principal component-like analysis PKA play in confirming the feasibility of the machine learning inversion process, particularly in relation to the scattering functions and the underlying polymer states?
Principal component-like analysis PKA so acts like a detective that helps us understand the most important features in our data. In the context of the machine learning inversion process for analyzing scattering functions of polymers, PC helps confirm that our approach is working well. So when we collect data from our polymer experiments, it can be quite complex, like a big puzzle with so many pieces. PCK simplifies this complexity by identifying the key patterns or directions in the data that explain the most variation. So think of it as finding the most important clues that tell us how the polymers behave under different forces. So, by using PCA, so we can see if the scattering functions and the underlying states of the polymers are aligned with what we expect. If PCA shows that the main features of the scattering functions correspond well with the physical parameters we're trying to extract, it just confirms that our machine learning method is probably on the right track. Furthermore, PCA also provides additional insights like the characteristic orientation of the scattering function, which just adds more value to our analysis. When we see that the feature parameters really extracted by the machine learning method so closely match those calculated through Monte Carlo simulations, it gives us confidence in the accuracy and feasibility of our approach. In simple terms, PK helps us ensure that we're reading the clues correctly and that our detective work in understanding the polymers is so successful.
Could you just describe the training process of the Gaussian Process Regressor and how it utilizes the dataset to extract the feature parameters like bending modulus, stretching, and shear forces from the scattering data?
The training process of the Gaussian Process Regressor. So GPR is like teaching a smart assistant how to recognize patterns in a collection of data. In our case, we want this assistant to learn how to connect the scattering data of polymers to really important physical parameters like bending modulus, stretching, and shear forces. First, we create a data set using Monte Carlo simulations. So this data set includes different scattering functions, which are like snapshots of how the polymers behave under various conditions defined by the energy parameters. Each snapshot corresponds to specific values of like bending, stretching, and shear. So next we divide this data set into two parts. One part is used for training the GPR, and the other part is reserved for testing how well the GPR has learned. During the training phase, we feed the GPR the scattering functions from the training set along with their corresponding energy parameters. So it's like showing the assistant so many examples and telling it what each example represents. The sort of GPR uses a mathematical concept called a Gaussian process, which is a way of modeling uncertainty. It really defines a prior mean function that represents what we expect the relationships to look like in a kernel function that helps measure how similar different data points are. So this allows the GPR to learn from the training data and make educated guesses about the relationships between the scattering functions and the feature parameters. Once the GPR is trained, we test it with the remaining data to see how accurately it can actually predict the feature parameters from new scattering data. If the predictions closely match the values calculated through Monte Carlo simulations, it shows that the GPR has successfully learned the patterns and it can reliably extract really important information from the scattering data. So, in summary, the GPR training process involves teaching the model to recognize the connections between scattering functions and physical parameters, allowing us to gain insights into the behavior of mechanically driven polymers just based on their scattering data.
So what were the key findings of the study regarding the effectiveness of the Gaussian Process Regressor in extracting feature parameters? And how do these findings contribute to the understanding of mechanically driven polymer?
The key findings of the study regarding the effectiveness of the Gaussian Process Regressor. So GPR in extracting feature parameters are quite promising. The GPR successfully mapped the scattering functions to important physical parameters, such as bending modulus, stretching force, and shear rate, So this means that the model was able to accurately predict these parameters based on the scattering data, which is a significant achievement. So the results showed a strong agreement between the feature parameters extracted by the GPR and those calculated through Monte Carlo simulations. So this agreement is quantified by the coefficient of determination, which indicates how well the predictions match the actual values. A high score in this measure suggests that the GPR is so reliable for extracting important information from the scattering data. These findings contribute to the understanding of mechanically driven polymers by providing a sort of practical solution to a challenge in the field. Traditionally, extracting physical parameters at the molecular level from scattering experiments has been so difficult. With the GPR's ability to effectively analyze the scattering data, researchers can now gain insights into how these polymers really behave under different mechanical stressors. So this understanding can lead to better predictions of polymer performance in various applications, ultimately enhancing the design and utilization of these materials in real-world scenario.
So how do the results of this study potentially impact future research or applications in the field of polymer science and engineering?
So the results of this study have the potential to significantly impact future research and applications in the field of polymer science and engineering. By successfully using the Gaussian Process Regressor to extract important physical parameters from scattering data, researchers now have a powerful tool to actually better understand how polymers respond to external forces. This understanding is crucial because the mechanical properties of polymers can greatly influence their performance in various applications, so from everyday products to advanced materials used in industries like aerospace, automotive, and healthcare. With a clearer picture of how polymers behave under stress, so scientists and engineers can design and engineer new materials that are tailored to specific needs, such as improved durability, flexibility, or just strength. Additionally, the advancements in scattering experiments like Regression, combined with the ability to apply machine learning techniques, open new avenues for exploring more complex polymer systems. So, this includes studying polymer brushes, star polymers, and polymer melts, which could lead to innovative applications in materials that we have not yet fully explored. So, moreover, the methodology developed in this study can be adapted and modified for other types of polymer systems, so allowing for a broader range of research opportunity. So as researchers continue to refine these techniques, we can expect to see enhanced materials that are optimized for performance, ultimately benefiting various industries and applications. In summary, so this study paves the way for future innovations in polymer science by providing new insights and tools for material design and analysis.
So thank you all for joining us today. What a fascinating dive we've had into the intricate world of mechanically driven polymers. We've just explored just how crucial it is to understand their behavior under external forces, and specifically the power of analyzing their scattering functions to unlock vital physical parameters like bending, modulus, stretching, and shear forces. Our whole discussion truly underscored the innovative approach of using Monte Carlo simulations alongside a sophisticated Gaussian Process Regressor to accurately map complex scattering data to these parameters. So, the reliability of this method, further validated by principal component analysis, marks a significant step forward. Ultimately, this research not only deepens our fundamental understanding of polymer mechanics, but also equips us with really powerful tools for enhanced material design and performance. The potential for innovation across diverse industries, from aerospace to healthcare, is truly so exciting. So thank you again for tuning in. So, we look forward to seeing you next time.